So we're going to talk something about clouds, precipitation, and get a little bit into what weather radar is all about today. You've learned a lot about moisture in the last video, so we're going to take it and try to understand how clouds form and how precipitation develops out of these clouds. If you'll notice, many times you get clouds and no precipitation whatsoever falling. So let's look at some reasons why that might be. So we know clouds are condensation. In other words, they are water droplets that have formed, or they're ice that is formed in the sky. They're no longer water vapor, because water vapor you can see through. So, how do clouds form? Well, interestingly, there is something called a cloud condensation nuclei that's needed to form clouds. So here you can look at the average aerial coverage of clouds. Notice there's a decent amount of clouds along the equator here, tropical convergence zone, and there's some over the oceans as well. Sahara Desert, almost nothing. There's a desert over here off of Chile that has not much. Southwestern U.S., not a whole lot of clouds. So you can really see how clouds vary around the globe a little bit here. So in order to form a cloud, we need a cloud droplet. Cloud droplets are really, really tiny when they develop. So with that being the case, they have a really sharp curve to them on their surface. And interestingly, that changes what the saturation vapor pressure is. All the saturation vapor pressures we talked about in the last video are all on a flat surface of water. Well, that would be the case in almost anything except these tiny little droplets. They're not even the size of rain droplets. And because they have that strong shape, they tend to lose molecules quicker back into vapor. So that the actual saturation vapor pressure is almost 400 times that of what you would require on a flat surface. So that would say, hey, we're never going to get a cloud. But there's something called cloud condensation nuclei that allow us to have a cloud. But what happens is these cloud condensation nuclei, which may be a form of dust, it may be a form of salt from the ocean, are up in the sky and water condenses on them. This creates a solution that actually reduces saturation vapor pressure significantly, bonds this little tiny cloud droplet together, and allows clouds to form. So there's two aspects to this. There's the curvature aspect and the solute aspect, both of which we just discussed. And here you can see how the difference between the two works. And what that curvature effect did to the model. Notice how it's very, very tiny. And it becomes much, much more difficult to get saturation over a strongly curved surface than over anything else. So rain droplets don't have this in problem. These are only droplets that just form the clouds. So we're going to move on here. These nuclei, as I've stated, can come anywhere from sea salt to dust. There are various forms of them, and depending on where you are in the country as to what type will be most useful. So they're also, interestingly, these water droplets don't freeze very easily. So cloud droplets can actually remain liquid all the way down to around minus 34 degrees Celsius. So how do we get snow in the clouds? Well, again, there are what's called ice forming nuclei. They're slightly different than the cloud condensation nuclei. When they arrive into the clouds, and they're always there, what happens is surface water around -9 degrees begins to freeze on these ice deposits. Once it begins to freeze, the ice begins to spread to other parts of the cloud, and we wind up with a lot of ice at about -10 degrees Celsius. So, interestingly, a lot of the water initially in the cloud is liquid, even though the temperature may be below freezing. So, we have a lot of supercooled water. If you get to -39 degrees Celsius, instantly all water freezes. That's not happening a lot in the clouds, but it does happen sometimes. Generally, you're going to need this ice nuclei. So now we're going into precipitation. Now that we've got a cloud, we have ice in one part of the clouds, another part of the clouds, water vapor, or not water vapor, just plain old water. We want to know what's causing precipitation to occur. Well, these cloud droplets don't come down to Earth unless they're big enough. They got to be big enough so that the air, which is helping these clouds to form, that's rising, will be overcome by the mass of these water droplets. And once they do start falling, gravity will pull them down and increase their velocity to where friction with the air around them will reach a point that will keep this what we call terminal velocity. They'll only be able to go that fast. Depends on the size of the raindrop, the type, the shape of the raindrop. Hail's case, the bigger the hail, the faster it's going to fall down. All of that reflects in this terminal velocity. So how do these cloud droplets form and make precipitation? There's two processes. There's a collision coalescence and the Bergeron-Findyson effect. If the clouds are all above freezing, we have a warm cloud. They're all water droplets. So what happens? Well, what happens is little tiny droplet, maybe just a little bigger than the one next to it, and just touches it, touches the other one. Well, it absorbs that one. Then it absorbs another one. It gets big enough, it begins to drop a little bit. As it's dropping, it hits other tiny cloud droplets and grows some more till eventually it gets big enough that it's able to fall out of the cloud and fall down to the ground as rain. So this is just one process, a very efficient process. It can give you the heaviest rain sometimes because there needs to be a tremendous amount of moisture in the air to have this process work. Now, on the other hand, interestingly enough, almost all precipitation in our clouds up where we live form and begin as ice crystals or snow. So we're going to go and look at why that is here. What we want to know is why. So what happens with this is that we wind up with these ice crystals having saturation vapor pressure slightly lower than the little tiny raindrops that are there. So as that happens, the moisture shifts into the ice that's rapidly forming due to the ice condensation nuclei, develop, they grow, and they become the predominant form of precipitation at that altitude in that cold air. So that we begin with ice crystals freezing a little tiny droplet somewhere. And when that does, it takes away all the moisture from the rain droplets and pushes it into each one of these ice crystals. So the ice crystals grow, get bigger, and then they begin to fall out of the sky, come down to where they can melt, and continue on down to the ground as rain. And you see here, rain is just one of the things here. We also can have drizzle out of the clouds. And there are different shapes to these ice crystals as well. If you're forecasting snow, believe it or not, you got to know what the shape of the snow is. We have what we call dendrite snow. You'll notice here it has the biggest area it covers, even though it's the same amount of liquid. And you also have thin plates or solid prisms of snow. Well, if I am forecasting snow and I tell you you're going to have 6 inches of snow and you have dendrites, and I'm forecasting using that, okay. However, instead, maybe you have these sectored plates or other things, other shapes with that snow instead. Then that's not going to take up as much room. So instead of having the 6 inches, maybe you only get 3 or 4 inches. And that is a bad forecast. So we try to figure out what kind of snowfall we're going to receive. The heaviest snowfalls we get are with dendrite. So if I have precipitation forming in a cloud, and we're going to assume we're up at our latitude here, where typically most clouds are going to be below freezing. We're going to have ice in them. We wind up getting some snow in that cloud. Begins to fall. At some point, as it's falling, most of the time, especially not in the wintertime, the precipitation is going to hit a warmer layer above freezing. It will melt and come all the way down to the ground as rain. In the wintertime, maybe there's some cold air left. Remember, warm air rises and it goes over top of cold air. Well, if I'm haven't got a warm front through yet, but there's precipitation coming and has moved over my area, the bottom area might have ice. So that's where you get your freezing rain. Yes, above it, temperatures above freezing. I've used this at times in the mountains in West Virginia when we're driving. We wanted to get out of an ice storm that was just starting. We would drive up to the higher elevations in the mountains and get above the ice. So that is one way it can actually benefit you. If the layer is thicker, we get more in the way of sleet. If there's no melting or a very teeny tiny little bit, it's all snow. So we have to understand the temperatures in the upper atmosphere in order to tell the precipitate type, especially in the wintertime. Hail, big lumps of ice, and it can be really, really big, bigger than a grapefruit. What happens is the updrafts in a thunderstorm lift ice pellets up and down they go, eventually gaining more and more liquid on them. So eventually they become hail. We showed you a little bit about the freezing rain and how that works. So one of the ways we detect the precipitation is by using radar. Radio detection and ranging. Radar emits microwave signals. They emit it and then they listen. They spend 95% of their time listening. So as they're rotating around, they send out pulses of energy, and the rest of the time they're listening for that energy to come back to them, where it is bounced off a cloud, dust particles, precipitation, whatever. We tune it so we try to look just for precipitation. But sometimes we pick up other things as well. We may even pick up birds migrating out of a lake. But the radar listens. It has to know how far that signal has traveled out and how long it took to come back, and then it can calculate where it's at. And radar goes out in a flat line. We started at 0.5 degrees, and it just goes out straight from there. But the radar can elevate too. So what we do is each scan, each time around, we gradually lift the radar higher and higher up. So we're looking over a bigger and bigger volume of area of the air. That way we can see how high up in the clouds maybe a thunderstorm goes. Whether there's new precipitation beginning somewhere up in the clouds and hasn't come to the ground yet. And because we're doing Doppler radar, we can take the Doppler effect into account and determine the velocity. So we have reflectivity mode that detects these areas and intensity of precipitation, and Doppler mode determines whether the air is moving away from my radar or towards my radar. That's what it detects. So here is like a dome. Uh, they're up in air a little ways so you don't wind up any of this microwave really hitting the ground. And the Doppler effect is the same as if you listen to a car go by you or a train. It just changes its sounding. So, how do we utilize this? Well, let's look at a radar reflectivity here. You can see the most intense precipitation is right in this area. We can see the shape of the precipitation. That's just all what we got from reflectivity. When I came into Weather Service, that's all we had. We didn't have Doppler radar. So if I was looking at this, I would say, well, this shape is kind of like a low pressure system almost. So maybe there might be severe weather with this shape. Well, now with Doppler radar, I can actually see the motion of air and I can see there's a circulation of air right there, very tight together. And finally, we just went to phased array, which allows you to look at two-dimensional picture of these raindrops or whatever it's looking at. So it can actually pick up debris. So now it's seeing debris in the air, indicating this tornado is on the ground, which all came out of this circulation right here. So by utilizing three different products within the radar, I get a complete picture now of where there's possibility of a tornado. This debris signature may not always be there, and we're trying to obviously forecast the tornadoes hitting the ground. We want to get a warning out before it hits the ground. So here you can see a tropical system coming in to North Carolina and the Outer Banks. You can see the winds here. Finally, there's a system called phased array weather radar. Not out there anywhere yet. The reason it's not out there, it is very, very expensive to build. However, where I talked about the radar doing a scan every 5 minutes upwards, phased array is instant. It has high resolution and it looks in every direction instantly. By doing that, you're detecting things in the cloud much quicker. You may gain 5-10 minutes and more detail. So it is a system that may come someday, but it's going to take a long time because of the cost. So one way of measuring precipitation is tipping buckets. What happens is you have a little thing in a bucket, literally that tips, lets the rain drop fall down to below it, and it will measure each 1/100th of an inch of rainfall. We measure snow depths by using a ruler, and we go out and clean off a board and measure on that. Typically, it's 13 inches of fresh snow to 1 inch of water, but that can vary significantly. Weather radar can actually give you an estimate of precipitation as well in some areas. And here you can see that an estimate around New Orleans and all of how some tremendous rainfalls moved into that area. All right, finally, just a quick look over some cloud classifications. High wispy clouds are generally cirrus form. Stratiform are layered. We talked about that at the very beginning of the course. And cumuliform clouds are a little bumpy. Warm clouds, temperatures above 32 degrees. Cold clouds, temperatures below. And you can see here on cirrus clouds, they may be thin. Cirrostratus is a little more layered cloud, and cirrocumulus is actually bumpy. And this is high clouds. These are all ice. And these may be well up in the atmosphere. And you see the alto cumulus. Alto just means middle of the atmosphere. These are middle clouds, and you can see their cumulus here and altostratus there. Finally, we get down to lower stratocumulus, little bubbles of clouds, but no real big ones. And here's stratus is like a fog deck or nimbostratus where it's precipitation. And finally, these clouds develop, if they develop by convection, which is what a cumulus cloud does, the bottom altitude of that is to the convective condensation level. It's the altitude at which convection lifts the air, it begins to condense. And you can see here, clouds actually having the vertical development right in this area, and some areas not. And clouds moving across the Great Lakes as well here. If you were looking for lake effect snow, and I lived in this area of Ohio, I'm looking for cloud streak coming down off of Lake Ontario, Lake Huron, excuse me, and across Lake Erie. Two lakes provide more potential for water. I'm going to get heavier snowfall. So I think that's altocumulus lenticular clouds as well. These are clouds when they develop on the downwind side. So the air is actually become bumpy on that side. If you're flying an aircraft, you can run into these kind of clouds that really hit a lot of turbulence. So hope you got something out of all this. Please ask me any questions.